continue working hard. And end of December, your report is also due for NASA, ULI, and others. Okay, it is really my pleasure to introduce the next speaker. Chanel is one of our PhD student that she's part of NASA ULI project. And let me just say a few things about Chanel. She received her bachelor degree in aerospace engineering from MIT in 2015, followed by continuing her education. What is that? In Imperial College London, received a MS in control systems. Currently, she's pursuing a PhD, her PhD at the School of Aeronautics and Astronautics at Purdue University. Her research interests include high performance nonlinear control, adaptive robust control, reinforcement learning control, and data-driven optimal control methods. With respect to application, her interests include flight navigation and control for unmanned aerial systems in mixed cooperative competitive environment. I like to also say another thing about Chanel is she's the chair of our student leadership committee. With that, Chanel, I'm going to let you start your talk.
Thank you, Professor Hamafar.
Pleasure.
Thank you. So I will go ahead and share my screen really quickly. Let's do that. Can everyone see my screen?
Yes.
Okay, great. Thank you for the introduction. As Professor Hamafar said, I'm Chanel Clark, and today I will be talking about my thesis work or my dissertation work with the title Towards Provable Guarantees for Learning-Based Control Paradigms. So today I will be mostly focused on the introduction and background sections, identifying research gaps with respect to adaptive control and reinforcement learning, and how these learning-based control paradigms differ, and what my preliminary work has been towards bridging some of the gaps in the literature. And then I will, yeah, that's what my talk is going to be on today. For the sake of time, since my prior work has so many sections, I'm going to be focusing on part 3, where I specifically talk about learning from expert demonstrations. So, hello?
Yes.
Oh, I thought there was a question.
No.
Okay. So adaptation is a term that has been long since defined in evolutionary biology as the advantageous conformation of an organism to its changes in its environment. And so therefore we can talk about learning as a type of adaptation, specifically the spatial temporal adaptation in which there's a sequential betterment in performance gained from behavioral modifications that result from information feedback from your operating environment. That sounds like quite a mouthful, but let's put it in the context of engineering applications. So within the engineering context, Bellman in 1959, on his work in dynamic programming, defined an learning-based control as a controlling element that learns to improve its performance based on experience gained from unfolding information, given some uncertainty on the system structure. And so we can look at the adaptive control architectures that was prevalent during that time. And we can even think about the fact that when it comes to learning-based control methods, one of the main, the earliest motivators of learning-based control, specifically adaptive controllers, was in the aerospace industry, because these systems operate under different operating conditions, different flight regimes, and in such uncertain environments, it makes sense that we'd want to develop some kind of control paradigm that would be able to adjust based on the input that it gets or the stimuli it receives from its environment. And so I'm going to we can talk about uh, this case where I think it was Athena Technologies. Essentially, they discharged or uh, lost a section of their wing profile and was still able to fly um, after its plans had changed by so much. And so we within control theory, learning has manifested itself in terms of model reference adaptive control. And I have here a chronology of the different concerns that adaptive control has addressed over the years. So as early as the 1950s, researchers were looking into adaptive control for deterministic and continuous time systems, looking at linear systems. And then we had a huge milestone in the development of the MIT rule. After about 1965, researchers realized that more work needed to be done on adaptive control in terms of the MIT rule because it could be unstable. And so we started thinking about Lyapunov methods and self-tuning regulators. And there was also a concentrated interest in adaptive control towards stochastic systems. After about 1985, we started thinking more about time varying parameters, adaptive robust control, having bounded disturbances, looking at increasingly more nonlinear systems, and even thinking about not just uncertain parameters, but also unmodeled dynamics.
Sanel, which is the MIT rule?
The MIT rule is the gradient descent rule. Yeah. And then from the 90s to about now, there's been a lot of emphasis in data-driven adaptive control methodologies, as well as compensating for state and input constraints and looking at time delays into a system. How can these different effects cause instability in our system? However, an adaptive control is, sorry, yeah. So we can also think of another type of learning based. So at the same time, reinforcement learning and dynamic programming was being developed alongside adaptive control methodologies. So it was around the 1960s where the perceptron and neural nets were being introduced, and we had algorithms on TD learning, that is temporal difference learning. And then uh, that, yeah. And then it wasn't until the late 1980s where we started, where reinforcement learning became a thing. And so reinforcement learning is a subtype of machine learning in which an agent interacts with a possibly stochastic unknown environment via trial and error experiences in order to improve its performance. And so we can see the analogy towards adaptive control, the same element where we have a learning paradigm that looks at an uncertain or possibly unknown environment and seeks to move in a direction of better performance. However, based on the chronology that I have here, you can see that reinforcement learning methods have not grown as rapidly as adaptive control methods. And we can get into the reasons why that is so, but from my research, it's partially because of hardware constraints. Reinforcement learning is a numerical algorithm, and has a large non-asymptotic properties, which I'll address a little later, that kind of constrained the systems or the hardware, sorry, that overwhelmed the hardware prior to the 90s. And so we have the general adaptive control architecture where we have some reference input, we're generating a control through this uncertain system, and then we have the feedback loop, but there's also this element of parameter adjustment where we take that control input and the output from our environment, and then we adjust our controller parameters to be able to operate within this uncertain system. And comparatively, we have the reinforcement learning architecture where the environment is entirely unknown. Instead of what we call the output or the error in adaptive control, in the adaptive control architecture, in the reinforcement learning community, they call it rewards. So we interact with our environment via an action, we receive a reward, we update our states and our controller, and then we modify our actions so that we'll get increasingly better rewards. And so I found a talk by Professor Ben Recht on the internet when I was scoring, and he had this really interesting philosophy that I thought I would share. Essentially, he says that in the controls community, they look at reinforcement learning as a subset of controls, whereas in the machine learning community, they look at controls as a subset of reinforcement learning. And so he had some interesting discussions on why that was so. However, from the literature, regardless of who is a subset of whom, it seems that adaptive control and RL tends to solve the same problems. In fact, it was back in if I go back to this chronology, in the 1980s that reinforcement was referred to as direct adaptive optimal control. And so we're looking at solving the same problems from different perspectives. Within the RL community, they really emphasize performance, maximizing your rewards, whereas in the controls community, a lot of focus is spent on ensuring what we call control theoretic stability. And I use the word control theoretic because I do not want it to get confused with numerical stability, which is also called convergence. And so I'll keep referring to it as control theoretic stability for the rest of this talk. And so one of the biggest fundamental difference, and this was, and we can think of this as having been established way back by Bellman, is the idea of the degree of system uncertainty, where adaptive control and RL essentially exist on two ends of the spectrum. And I specifically refer to model-free RL or direct RL, where the system is completely unknown. Whereas in adaptive control, the system structure is very well defined, but you might have parameters that are uncertain or within some set that is known. And so let's take a look at the research gaps between model reference adaptive control and model-free RL. So we first see that there's a difference between the certainty of the model considered in both paradigms. However, we can also look at how this uncertainty in the model affects the performance or the guarantees that are prescribed or the provable properties of each of these learning algorithms. So first and foremost, we see a difference in performance. So in adaptive control and in control theoretic methods in general, we tend to make simplification assumptions on highly nonlinear dynamics to be able to nicely analyze the stability, the stable performance of the system. So to be able to guarantee either asymptotic stability or global upper boundedness. And so the more nonlinear the system is, the more difficult it is to prescribe these guarantees. However, in RL, because they do not care about, well, I shouldn't say they do not care. The emphasis is placed more on performance, and it's really difficult to analyze a black box system, which is essentially what they have with an unknown model. Yeah, sorry. Yeah, so sorry, I need to backtrack a little bit. I think I got ahead of myself. I'm talking about the performance of adaptive control methods and RL methods. And so we've seen a lot of recent successes in RLs, from AlphaGo to autonomous driving. And this idea of having a completely unknown model enables it to kind of search a wide design space for a truly nonlinear controller that has the potential to improve overall performance. And so there's no simplification on the nonlinearities needed. Yeah. So we can look at the difference between both methods with respect to the specificity of the system. And so with adaptive control, the controller design is strongly dependent on the class of models. If the model is linear or nonlinear, or if there are specific assumptions on the type of nonlinearities that are embedded in the model, the control designer would then change. However, with RL, since it's just it's agnostic of the model is unknown, and so the architecture is pretty generic for all system models and types. And we can basically write a state to input structure for any type of any type of system model. Okay. And then we can talk about also control theoretic stability. So MRSE methods specifically emphasize control theoretic stability guarantees. How the controller is going to work on deployment, what are the asymptotic guarantees that we have, looking at the transient properties of the trajectory tracking error are very important in this community. With respect to RL, recently there's been some work on proving control theoretic stability for linear systems, specifically looking at the LQR problem. However, the large emphasis remains on eking out better performance of our systems as opposed to guaranteeing some stability condition. We can talk about the gaps in the literature with respect to constraint satisfaction. So with respect to adaptive control, as shown by the chronology, there has been recent work in looking or developing adaptive control methods for state and input constraints. However, for RL, there are few methods that look. It's an open field of work. There are papers coming out every year about how to design an RL architecture that is able to satisfy hard instantaneous and or cumulative constraints. However, it's a very difficult problem because of the black box nature of the model. And then we can also talk about convergence proofs. So this is numerical stability, convergence of the algorithms. For MRSE, these are typically guaranteed. For RL, there are increasingly more works that prove convergence for linear and some nonlinear systems. However, it's still one of the active fields of research within the RL community. And last but not least, I'm going to be paying attention to what we call the non-asymptotic guarantees. That is, if you are dealing with a data-driven method or a method that utilizes data to derive some controller architecture, we need to talk about what the performance of your controller will look like in the face of a finite data set. So a lot of the methods in RL have high space, sample, and computational complexities. And by a space complexity, I mean it requires a lot of space. It requires a lot of storage to be able to accumulate large amounts of data. With respect to the computational complexity, it is with respect to your algorithm, does it finish in linear time? Does it finish in polynomial time? That kind of analysis. And then for sample complexity, it talks about what is the performance gap given a finite data set. So if you have a data set that is small, what would be your performance gap in that case, as opposed to one that if you had like twice the amount or even 4 times the amount. And so in general, RL methods have high space, sample, and computational complexities, whereas MRSC methods by nature are low and inefficient, have low space, sample, and computational complexities. And so we're going to be looking at these gaps. So we're going to take a look at, these research gaps are going to define my research objectives. So we're going to be looking at the differences in performances, looking at can we develop methods for more nonlinear systems and nonlinear function approximators, control theoretic stability. Can we prove that for RL algorithm, given that MRSC methods already have proofs on control theoretic stability? For constraint satisfaction, can we develop MRSC and RL methods that guarantee the satisfaction of hard constraints on the state and inputs? We're going to be looking at convergence issues for RL methods. And also we're going to be looking at the non-asymptotic. Can we provide non-asymptotic guarantees for reinforcement learning or RL methods? And so these are going to define our research objectives. The first being, we would like to develop a model reference adaptive control algorithm for a more general class of constrained nonlinear system. So essentially, this objective is tied to widening the class of nonlinear systems considered by RL, since this method is so system specific and dependent on the model. And so we need to be able to consider the effects of, let's say, uncertain parameters, a lack of full state information, and external time varying disturbances, and be able to prove stability in that context. The second objective is to develop RL methods for a more general class of nonlinear system and nonlinear function approximators. I included IRL in this slide, but I think it's slightly out of order, so I'll touch on IRL in a second. The third objective is to provide a provable finite, hopefully, preferably low, sample space and computational complexity analyses for RL and IRL algorithms. The fourth objective is to develop constrained RL algorithms that have provable guarantees on convergence, hard safety constraints, and control theoretic closed loop stability. And last, we want to validate and demonstrate the comparative performance of these methods on real-world flight control problems. This slide is slightly out of order, but we need to talk about it to go forward. And so inverse IRL is based on the concept of reinforcement learning, and it's the problem of inferring a reward function from an agent given its policy or observed behavior. This is different to RL because in RL, we're looking at given rewards, given interactions with our environment, how we need to develop some control policy or behavior, whereas in IRL, it is literally the inverse of that process where we look at state and input behavior and we're able to infer some reward function based on that. And so IRL in general tends to, it's tightly linked to reinforcement learning because we typically use the reward function to then find a controller. So we use a given data set from some expert trajectory. We would then infer the objective of the expert. And given this objective, we'd build an RL module onto the IRL algorithm to be able to then develop a stabilizing controller. And so IRL shares a lot of the same concerns as RL. So our discussion on the differences between MRSC and RL is also applicable to inverse reinforcement learning. And so for the sake of time, we're gonna talk about part 3, looking at learning from expert demonstrations, looking at RL. And because I've talked about these ones before, so let's kind of delve into something a little bit more new. So with respect to learning from expert demonstrations, we're going to specifically be looking at model-free stochastic inverse optimal control for the LQR problem. And so this section of my presentation satisfies objective 3, where we are looking at developing an inverse reinforcement learning method that is able to provide finite, low spaced sample and computational complexity analyses. But the question is, why are we even doing this? What is our motivation here? Why do we want to learn from an expert as opposed to some trial and error method or using adaptive control? And so the idea here is that instead of having to learn from scratch, you can learn how to control a system from the experience of an expert. And we typically assume that the expert is optimal. So given expert data, we then infer the performance objective, the parameters of your performance objective. And this allows us to inform behavioral models, which help us to predict future behavior, and also helps to characterize how these individuals make decisions. Inverse RL, or inverse optimal control, and I should tie those back together because model-free inverse optimal control is inverse RL. It gives a transferable definition of a task. So if we are able to infer the performance objectives, then these parameters, if we're able to infer the performance objectives, we can use that objective function and then be able to transfer it to a different task and learn a controller based on that. It might also allow us to ascertain why certain behaviors are preferred or more preferred than others. Why would an expert take an action X as opposed to Y? And so that might be related to, oh, well, this maps to a better overall or cumulative performance instead of an instantaneous performance. So those are that is information that is useful to have. And then this kind of all ties it together. If we are able to infer the performance objectives, we can then recreate and improve upon expert behavior. And if we don't want to go that far, it's possible that we might be able to recover the controller directly and use that directly. So the idea here is, given some expert data, we infer the performance objectives and possibly the controller, and we can essentially deploy it, and the controller is able to learn from the expert. And so what is the scope of this section? So as I've said before, we're looking at inferring the controller, or learning a controller and inferring the performance parameters from the inverse LQR problem. And I've sectioned up what the problem looks like in terms of the RL perspective and the controls perspective. A lot of the terminology is different, but the idea is the same. So if you're thinking about the state and action space from the RL perspective, they talk about having a continuous state and action space. That is, the actions that you take are not discretized, and it's some continuous variable. Whereas in controls perspective, we simply say that the state belongs to some Euclidean space, n-dimensional Euclidean space or m-dimensional Euclidean space. And for our problem, which I'll define the dynamics, we're going to be looking at the stochastic discrete time linear time invariant system. In RL, they talk about this is more or less equivalent to the stochastic stationary Markov process. And for the LQR problem, the expert is going to be an optimal linear controller. Our solution is going to be the controller gain and performance parameters. And the guarantees that we are especially concerned about is the well-posedness of the optimization problem. The well-posedness refers to how feasible the optimization problem is and how are we able to generate a unique solution. And we are concerned with having a unique solution because having a non-unique solution to our problem does not necessarily help us when it comes to inferring the expert's intent or objective. We're also going to extract a stabilizing controller and then look at and then we have designed a control method that is able to give us low complexities with the analyses provided. And so I'm kind of skipping over this because I kind of talked about it already, what the contributions of this work is. Analysis of well-posedness for stochastic inverse linear quadratic problems. In the literature, it currently only deterministic model-based inverse LQ problems have been provably well-posed. There are works on the stochastic problem. However, they haven't been proved to be well-posed. That is, they're not guaranteed to be feasible. And there is a significant gap with respect to analyzing the non-asymptotic guarantees and providing low finite complexities for the space, sample, and computational complexity. And so I'm going to give you the problem formulation for my inverse LQR problem. And so we're looking at a discrete time LTI system, as I previously stated. And we have some infinite horizon objective cost that looks at the steady state average over some asymptotic horizon. And our problem definition here in inverse LQR is to, if we're given a control policy that is a linear state feedback policy that generates a set of noisy trajectories, we want to be able to recover a stabilizing control gain, the stabilizing optimal control gain that is necessary and sufficient to minimize our objective function J0. And we want to determine the pair of unknown weights Q and R so that the cost function is minimized for every trajectory that we obtained from our expert, or that is within this set gamma. I want to point out that this notation, script KAB, is the set of all stabilizing feedback gains, such that the spectral radius of your, or the largest eigenvalue of your system is within the unit circle. We specifically emphasize that the matrices A and B are unknown. So this is a model-free method. We do not estimate A and B. We do not assume that it's known a priori. The only assumption we make is that the system has a structure as 56 and it is stabilizable. Also, the cost functions Q and R are known as per the inverse problem. I will give you a note on the numbers. So these numbers come from my prelim report. So it's really difficult to kind of transition that. So, but it will help us to reference the equations as we go through this. And so the system matrices and cost function parameters are unknown. So therefore we have to find a control gain K. We're looking to infer the controller and the cost function parameters using data. This is a key assumption that I make, that AB is stabilizable, and that we have a set of R trajectories where R is at least n plus m, where n is the dimension of the state, and m is the dimension of the input. And why I make this assumption will become clear in a minute. And we want these trajectories such that this matrix, and I'm going to call it the pseudo Hankel matrix. It's not quite a Hankel matrix. We want this matrix to be positive definite. What does that mean? It means that the set of trajectories that we get are sufficiently rich. That is, there is sufficient variation introduced into the trajectories that we've collected that it can meaningfully encompass the dynamics of our model. That way we can design a true model-free controller without having to infer the system parameters AB. So how do we get this matrix to be positive definite? We can think of the idea of persistency of excitation. So persistency of excitation is tied to the idea that we want to sufficiently vary the trajectories, the outputs of our system, the output trajectories of our system, so that we encompass the possible behaviors of our system. And so we can, if we add noise, it varies our trajectories. And then we can also use the initial conditions. So where we start, where we initialize our system can also help introduce some perturbations into the system trajectories that we consider. And so for the method that I develop, there are two sources of excitation of the system. And let me stop here and ask if anybody has any questions, because I know I've said a lot.
Thank you so much. It's really very helpful. I'm glad to hear someone at Purdue is also doing some work on model-free. You know, most people do their work on model-based.
This is true. And we can talk about why, but yeah.
Okay.
Yeah.
Now, you mentioned a couple of things in here,
Mm-hmm.
because this is something that also we are trying to address as well.
Mm-hmm.
Stability or convergence is very important.
Mm-hmm.
But you mentioned about potential on it was your slide, I believe, on slide 4, you
The
mentioned.
performance.
Yes.
Or improved performance.
Yeah, it has potential to improve, and then basically you are listing pros and cons
Mm-hmm.
for each of the methods that you are mentioning
Mm-hmm.
has potential to improve overall performance since no simplification. That is true.
Mm-hmm.
There is a cost also associated with it.
Yes, it is.
Okay, and also,
The design space that you're searching can be highly nonlinear and you may not be able to converge, which is why we spend a lot of time tuning parameters and trying to fix things. So we might converge to an area.
yes, and then you mentioned about, okay, yes, it's a function of whether we have a rich data that we can approximate the model. Because like
Mm-hmm.
in model base, you're assuming that here is the model.
Mm-hmm.
But what about, in data driven, you're assuming that somebody is going to give you the data.
Yes, correct.
So how do you guarantee this is where satisfiability and all that are playing in my mind, and you're addressing some of them are
Mm-hmm.
basic elements of what is needed in this domain, for example.
Mm-hmm.
Yeah, and I'm glad to hear that you are addressing some of these things. And then this inverse, uh, what is that inverse
Inverse optimal control or inverse RL.
RL? Yeah, inverse
Yeah.
RL. When you say inverse, inverse in a sense of what? Remember that when you're coming from model base, I know what inverse means, but what is the meaning of inverse in inverse of reinforcement learning?
So the inverse problem looks at given data
Mm.
or given uh, from the model tree perspective, given data, can we infer or can we recover the cost function parameters that describe our cost function? And then from that, can we then get a control design or a controller?
So basically, from the data, you want to come up with a model. Once you have the model, now then you can do everything that you want, right?
Typically, that's how it's done. In the method I'm going to present, I bypass estimating the model.
Mhm. Okay,
So that's what I mean by model free.
all right.
It goes directly from data to control design and um, recovering the objective function. So this is a little, yeah.
Okay, thank you.
My last point on this slide here is if we can satisfy uh, this, what I refer to as the pseudo Hankel matrix, um, if we can have it be positive definite, I'm going to show that this is the only matrix we need, or this is the certain definition of the matrix that we're going to use going forward, and that conveys a sample complexity of n plus m on our controlled design. So how we need to solve problems, subproblems P1 and P2. That is, recover a control gain and then determine the pair of unknown weights that parameterize the cost function. And so step one is how do we extract the control gain? So we have this idea of the sample marginal covariance of the data, which I'm calling XIR. And it's directly related to this matrix that I'd previously talked about before. And so we could think about it as the variance in the state and input data over n trajectories, over r trajectories of length tj. And I think I neglected to mention this before, but the assumption too that we have here assumes r trajectories and of varying lengths. So you can have R trajectories that my method does not require you to do extensive pre-processing, and you're able to use also partial trajectories. So using this estimate of the sample covariance of the data, it's really easy to see that we can extract the control gain from this parameter by simply examining the partitions of the the one step forward sample covariance. So if we start at some initial point kj, remember that I had specified that our starting conditions be varied. So from kj plus 1 onwards, where the controller, so the control input that's being used is the linear state feedback parameterized in terms of the control gain. And so looking at the partitions of this one step forward covariance matrix, we are able to extract the control gain in a pretty simple form. But how can we guarantee that this is positive definite? I know that I've made the assumption, but what does that mean in terms of the starting conditions and the sources of persistency of excitation, the noise as well. So here we need at least n plus, if we need at least n plus m starting conditions, or that is n plus m independent trajectories, or we need n plus m plus 1 independent noise vectors that is injected into a single trajectory. So if you have multiple trajectories of, let's say, length 2, then you need n plus m trajectories. However, if you only have a single trajectory, you're going to need n plus m plus 1, at least n plus m plus 1 points that have been sufficiently excited by the noise injected into the system for us to be able to say that 59 or sample covariance is sufficiently excited so that we can extract the control gain. And so these come from varying the trajectories, getting trajectories from varying starting points or varying the noise in a single trajectory. The next step is to recover, once we've had the control gain, we need to recover the a unique estimate of our parameters of our cost function Q and R. And so to do that, I propose solving the inverse problem P-inv in 60, where the solution of this would be the estimates QR and the Lyapunov SDB variable P. As you can see, 60 is an SDP, or a semi-definite programming optimization problem with respect to P, Q, and R. So the question is, I want to talk about well-posedness of this problem. And by well-posedness, I mean, is P feasible and does it admit a unique solution? And so I'm going to take a two-pronged approach. First, I'm going to talk about feasibility. So I'm going to show that there exists a non-empty set of solution to P inverse, and that the cost function JP inverse is finite and bounded. And then I'm also going to prove that Q and R, the recovered solutions Q and R, are unique. And this is based on some invariance theory. We'll get to that just now. But I do want to say that the problem P inverse, it's an SDP problem, and if you solve that using an interior point method, it admits at worst case computational complexity of polynomial in n plus m. And so by the way we've phrased the problem, we're able to get now low space complexity and low computational complexity. And then the next question we have is, can we talk about the last remaining non-asymptotic property, which is the sample complexity? And so how did we come up with this problem? It looks pretty random, but actually we take inspiration from the forward or the LQR problem. We know that if we consider the LQR problem with respect to our defined cost function J0 in 57, we know that that problem admits a solution that is the solution of the discrete algebraic Riccati equation. So K star and S star. And so we can talk about the non-empty solution set of the LQR problem omega 0. And so if we have some LQR problem with some cost function under our assumptions, this is in my prelim document. It's really difficult to it's kind of really difficult to put this into a slide because it's very theoretical, but we can prove that the LQR problem is equivalent to the problem P1, which is a differently parameterized form of the LQR problem in terms of this variable x and t, which is the averaged steady state covariances of the state and input information, as well as the sources of excitation of your system. And so, hope I'm not going too much over time. This problem satisfies some KKT conditions given Q and R. So the forward problem takes Q and R and gives you a solution K. And that solution K satisfies the KKT conditions. And so solving that KKT conditions gives you this non-empty set of with this control gain. Can we use this to essentially solve the inverse problem? And so P inverse, what if we go the opposite way, where we have the controller K, because we've already solved for the control gain from the set of data that we have. Solving the KKT conditions would then, for some non-empty initial set on K, would then give us the non-empty set on Q and R. And so essentially we're using we're using the LQR problem to inform the inverse LQR problem. And so, but how do you solve this in a model-free way if A and B are unknown? Typically, you'll see works that then estimate A and B, but we want to essentially bypass this method. And we're going to use the idea of the principle of certainty equivalency. That is, we're going to be using the sample covariance, the marginal sample covariance, as a minimum stress estimate of the true covariance X. And so from our definition of, and might have skipped over this, but our definition of Z here is actually the is actually the cross variance between the data at the current time step with the data at the next time step. I will get that down better, but essentially Z is the certainty equivalence form of A of K times the covariance. And so we're going to be using this idea of certainty equivalency to show that P inverse actually satisfies the KKT conditions. And so if we look at each of these equations based on these equivalency forms, the certainty equivalence forms, we can see that the equation on my upper left-hand corner, this equation in 60, satisfies the stationarity condition in 67. And we can just kind of go ahead and match up equations. Satisfying this equation would then satisfy the secondary stationary equation. We can satisfy dual feasibility. And then for complementary slackness, since the certainty equivalent form of X, this marginal sample covariance, is by our assumption positive definite, then this variable under complementary slackness, we could just let it equal to 0. And then the constraint on the primal feasibility actually comes from the dynamics. And so we're able to satisfy all the necessary conditions, the necessary KKT conditions. Yeah. And with respect to the sufficiency conditions, we just include the constraint that P22, which is the lower left-hand component of the P matrix, the lower left-hand block matrix of P. We just need that subcomponent to be positive definite. And so I have lemma 3. I can give you the reference for this because this is all in the paper as well. But equations might not match up. Yeah, by lemma 3, we proved that for a non-NT set containing our control gain and our data X, then the set of solutions to P inverse is non-empty and then admits a feasible estimate QR and dual variable P. And so let's get back to where we started. So we've shown that there exists a non-empty set of solutions. Now we need to show that the cost function is finite. With these two things, we can then prove feasibility of P inverse, and then we can move on to talking about what are some of the non-asymptotic guarantees that we might have. We also need to show the uniqueness of the solutions admitted. So I'm a little short on time. Am I still okay?
Still okay. You are
Okay.
still okay. Yes.
Okay. So we use this idea of certainty equivalency again to be able to prove that the cost function is finite. So we can think of, if we look at the cost function in 60, it's just a trace of the Lyapunov variable P. Given that P satisfies the equality constraint, I don't know if you can see my mouse, but the constraints such that such that the equation in the upper green box is the certainty equivalent form of the stationary equation in green, and that looks very much like a Lyapunov equation. And so we know that if the matrix A of K has its a spectral radius less than 1, that is, K is such that it stabilizes this matrix A, then we can use that equality condition to be able to write the matrix P as a geometric sum in terms of our lambda, right? And then we can go ahead and look at the upper bound on that because it's a geometrically converging sum, which is defined as P max. So so J in the cost function of this optimization problem is bounded, for one, lower bounded since P is positive semi-definite, and then is upper bounded by some value P max here. And so that takes care of the feasibility issue. And so we need to talk about the uniqueness of any solution that we get. So I specifically stated that this equation is a certainty equivalence form, which can be written in this way, since Z is equal to A of K, and X is a certainty equivalent form of the true covariance variable X. Sorry, XR0 is the certainty equivalence form of the true covariance X. And so we know that the Lyapunov equation is invariant under some similarity transform. So we can actually rewrite this equation in terms of some similarity transform. Yeah, in terms of some similarity transform that admits the same, well, similar solutions. And because it's invariant under the similarity transform, we know that these pre and post multiplying matrices must be commuting, since the columns of your transformation matrix does not provide the eigenbases for your invariant space. And so it uses the idea of the invariant space to prove that these matrix, so it uses the idea of invariant spaces to prove that these matrices must be commuting for the equations to be similar. And these commute if and only if the similarity transform matrix T inverse is a scaled identity matrix. And so any solution that we received from solving from this equality equation is scaled to some scalar is unique to up to some scalar ambiguity with respect to gamma. And gamma is bounded since our cost function is bounded. And last but not least, we can talk about the non-asymptotic properties of P inverse. And so I have a theorem on this, which I think is going to be a little bit more difficult to explain, but essentially, given the form that I've talked about, we can then I then provide the sample complexity bounds for the error between the sample covariance and the true covariance in these two equations. Oh, and so I have a similarity, sorry. So I simulated the performance of my inverse optimal controller, or my inverse reinforcement learning controller. Here with respect to quite a popular benchmark example that has unstable Laplacian dynamics. That is, the A matrices are very close to being unstable. And so we can look at the performance of your recovered, so this lambda is my recovered cost function parameters. So we can talk about we can see how the varying the number of trajectories and the length of trajectories actually improves performance. So the bluer it gets, the more accurate the cost functions that were recovered is to the true cost function, which makes sense. And in the paper, I have some more intuition on this graph, but for right now, I'm just gonna stop at this point. So, any questions?
Great, thank you so much. Thank you so
Yeah.
much.
Sorry, but it was quite dense.
No, it is great. And then you think you will be able to send a copy of your paper to us?
Yes, I can do that.
Okay, thank you so much.
Yes. But the equations won't match up to
No
that's
problem.
fine. Yeah.
No problem. No problem.
Mhm.
Okay, is there any question from cyberspace for Chanel? Okay, where is the application while people are thinking about asking question?
Where is the application?
Yes. What is your case study that you're going to be applying these things?
Oh, so I don't have this here right now because I need to put it in over the weekend, but I have a paper on fixed wing aerobatic maneuvering that I implemented with reinforcement learning. Specifically I used the normalized advantage function method from Lilycrap 2015. And I implemented it for So, okay. So in that paper, and I guess I could pull it up really quickly if you're interested in it. I might have slides on it actually from a previous presentation. I do. There we go. Not this one. That one. Tech cybersecurity. That's the same paper.
It's okay.
Yeah. No, I have it because I did a presentation on it. I've just been reusing the same slides for different things. Is it this one? Nope. Okay. Can't seem to find it.
No problem.
Mhm.
No problem.
So this is the end of my talk for today.